All right, so we just went through and determined what we're going to call the interval of convergence for this power series that we started with. So remember, power series defines a function, and we're trying to figure out the domain of that function by finding the values of x for which the power series converges. And so we ran the ratio test, and we used the conclusions of the ratio test to figure out what the limit means. And so we, want that limit that we got to come out to be less than 1 for the interval or for the series to converge. And that gave us an interval from -3/2 to 3/2 exclusive. And then when that limit is greater than 1, we know the ratio test tells us the series will diverge. And so that's bigger than 3/2 or less than -3/2. And then if the limit equals 1, the ratio test fails. So we had to go through and determine those two values, the endpoints of those intervals, and then look at those independently. And that's always going to be the case when we're working with these power series. We're always going to have to look at those endpoints separately and determine what's going on. It does kind of based on how the question is asked, but just keep that in mind. That we want to consider doing that. Well, we ended up with an interval, half open, half closed, as our values of x for which the series converges. And it turns out for every power series, there's always going to be a predictable way that it's going to converge, okay? And so we have a theorem that's going to describe that for us. And this is the theorem right here. Feel free to pause the video and write it down if if the way me talking over it's too much or whatnot. Okay, so for a given power series, and I'm using the general form, the sum from n equals 0 to infinity, c sub n times the quantity x minus a to the nth power, there are three possibilities. It'll always work out to be one of these three things, okay? And what three possibilities for what, and parenthetically for sets of values for which the power series converges. It's always going to be one of these three things. It could be that the series only converges at one point, x equals a, what we're going to call the center of the interval of convergence, or at the center of this series. Okay, so every single series will always converge at its center. For some of them, that's the only place they will converge. Okay, that's what number 1 is telling us. Okay, actually, all three of these together tell us that they'll always converge at A. Number 1 tells us that some will only converge at A. Number 2, the series will converge for all values of x, and A is included. So that means, all real numbers, -infinity to infinity. Some series will do that. And the third possibility is that there is a positive number r, capital R, such that the series converges if the absolute value of the quantity x minus a is less than r, and diverges if the absolute value of x minus a is greater than r. One way to think about this expression, and I'm going to give you some geometry for this, you can think of this as a distance, okay? So you're thinking of all points whose distance from a is less than r. That's for which the series will converge. But we'll talk about the geometry of that in just a moment. Again, I'm going to keep talking, so pause it if you are still copying and don't want to hear my comments while you're copying. So any power series will converge at A, and you'll see, that's pretty easy to see. If you go back up in here, imagine plugging A into this, A minus A becomes 0. And so, of course, sum of 0, an infinite number of times is still 0. Except for, the c sub n, as we talked about last time, a minus a to the 0 power, 0 to the 0, we're going to define to be 1. So you're going to end up with c sub n for this. I'm sorry, c sub 0 for this, that first constant. And we'll see that in some examples coming up. But nonetheless, every term after that first one is going to be 0. So adding 0 together that many times doesn't change the value from c sub 0, so it's going to converge. Again, some series will converge no matter what value you plug in, and some series will converge only, for values within a certain distance from the center. A few more lines for this theorem here. These sentences that follow are still part of it. This number r has a name. This number r is called the radius of convergence, and the geometry that I'm going to show you in a minute will hopefully illustrate why we call it that. But it's the radius of convergence of the power series. In part one, where the series only converges at x equals a, the radius is going to equal, I left this blank for a moment because I wanted to be able to let you think about it for just a moment. You should probably try to fill that in on your own, see what would make sense, what would be the radius if it series only converges at its center. Hopefully you've reasoned. Pause it if you don't want to see the answer just yet, if you want to think about it a little bit longer. But it is 0 because you're at the center is a, and you're not moving at all from a to get any points that any other values that for which it converges. So radius is 0. In number 2, the radius is r equals. Again, I'm going to give you the answer in a moment. You should think about it for yourself and find out if you can come up with an answer. But remember, the series in number 2 is going to converge for all real numbers, and so this is going to be an infinite radius of convergence because you can go as far as you want to the left or right on the number line, and you'll find values for which the series converges indefinitely. Okay, continuing. The set of all values of x for which the power series converges is the interval of convergence of the power series. And so some questions will ask you to find the radius of convergence. So you just got to find that r value. Some will have you find the interval of convergence. So you got to find, like we did in the previous example, all the values of x for which the series converges. So you got to make sure you read the question carefully and understand what is being asked of you. Some will ask you for both, so you'll see that as well. Okay, so that's our theorem. Let me see what's next. All right, so just to reiterate some things, the series, in number 1, the series converges only at a single point. In number 2, the series converges on the entire real line, all real numbers. And in number 3, there's a positive number r. So far, let's I'm not going to restate it. Let's go down to the geometry of it. So think about a number line, okay? When we have our power series centered at a, okay, then what we're looking at here is convergence guaranteed at a for reasons already stated. And then we're looking at part 3 right now. So if we think about this, change colors. If we think about this relationship here, okay, I said a moment ago that this represents all the values of x whose distance from a is r units. Okay, that's another interpretation of the absolute value that I don't know if that gets brought up enough in earlier classes or emphasized enough, but it's a good way to interpret what's going on. So if you think about that statement, all values of x whose distance from a is less than r, which means if I go r units in each direction, so if I go over here r units, so this becomes a plus r, and I'm not measuring, so I'm just going to approximate. If I go over here r units, so this is going to be a minus r, then this inequality up here represents all the points from here to here, because those are all the points whose distance from a is less than r. Okay, if I measure this length right here, this is r units away, as is this length over here, this is r units away. And so if I pick a point like right here, the distance between this point, I'll call x sub 1 for a moment, and a is less than the distance between is less than r units away. Let me say it that way. The distance between x sub 1 and a is less than r units away from a. And same thing over here. If I pick an x sub 2 over here, the distance between a and x sub 2 is less than r units away from a. And this is why r and the letter r is used, and why it's called the radius of convergence, because we're going equidistant from the center. And if I draw a very poor circle, which gets resized by the program here to look more like an oval and miss the points, which is fine. we're moving a set distance away from the center, a common distance, a radius, and everything within that circle, if this was a circle, would be points for which the distance from A is less than R, or points on which the values of X for which the series converges. Okay, I'm going to actually get rid of that oval because it just doesn't look good in the picture. Let's continue for a moment. The number 3 also says that if the absolute value of X minus A is greater than R, that's where the series diverges. Well, what does that mean? Well, if I go out here to say X sub 3, the distance between A and X sub 3 is greater than R, and so the series isn't going to converge there. And similarly, if I pick some point X sub 4 out over here, the distance between X sub 4 and A is greater than R. So if I look from this point onward, put an open circle at A minus R, and go in this direction, the series will diverge for those values. And if I put an open circle at A plus R and move in this direction, the series will diverge, okay, for those values. And this is consistent with what we saw back in the earlier example where we got the interval of convergence to be between -3/2 and 3/2, excluding -3/2 and including 3/2. I'll talk about the endpoints in just a moment, but nonetheless, the center of that power series was 0, and we went 3/2 to the left, 3/2 to the right, and everything within those two values were values of X that for which the series converges. Now, what this theorem doesn't give us is what's happening at the endpoints. So you have to make sure that you test the endpoints separately. Okay, test endpoints, like we did in that example. Okay, test endpoints. Because the theorem only gives us the strict inequality that guarantees those values of X for which the series converges. The absolute value of X minus A is less than R. It doesn't say less than or equal to. And that's because of the ratio test, because the ratio test doesn't tell us what's happening at those endpoints. Those are the endpoints for which the limit becomes 1. And when the limit becomes 1, the ratio test doesn't give us a conclusion. We have to test those things separately. Okay. So this is the geometry of what's happening here. And I hope this is a little bit clearer of understanding. Just keep in mind, anytime you have a power series, one of 3 things are going to happen. It only converges at the center, A. It converges for all real numbers. Or third, it converges on some intervals centered at A, and then you move R units to the left, R units to the right, and then test the endpoints, and everything from R units to the left and right within that distance, it converges at that distance, meaning at the endpoints, test separately. Okay, and that's how we're going to approach looking at all these power series. All right, let's try example number 2. Find the radius of convergence of the power series, the sum from n equals 0 to infinity, n factorial x to the n. All right. Ideally, now it's your turn to pause the video and see what you can come up with. It's always better for you to try than just to wait for me to do it and think you understand exactly what's going on. You get a better understanding if you try and don't succeed because you understand where you messed up, where you failed, and what you need to learn, versus just watching me and thinking you would have been able to do that completely on your own. So pause the video and go try it. I'm going to drop a hint in about 3, 2, 1. Here's the hint. If you haven't turned off the video, now do it. Use the ratio test and then see what comes out. See what kind of conclusion you can come up with. All right. Hopefully you're coming back from trying this on your own. And as I said, we're going to use the ratio test. So I need the limit as n approaches infinity. The n plus first term, which is going to be n plus 1 factorial x to the power of n plus 1. This is not a fraction, so I'm going to set this up as a ratio here over the nth term at n factorial x to the n. We have some things that do cancel here. This is going to cancel, leaving just an x in the numerator, and this cancels, leaving an n plus 1 in the numerator. And so I think rather simply, you'll be able to see now n plus 1 is positive. So I'm going to just apply the absolute value only to the x term. And then as n goes to infinity, of course, n plus 1 goes to infinity. Doesn't matter what x is. This is going to go off to infinity. So the limit does not exist. So what does that tell us? If you go back to the ratio test, well, it's telling us that the series diverges, okay? And so what's our radius of convergence here? I'm pausing, letting you think, letting you try to answer the question. It's not infinity, okay? Remember, the radius of convergence being infinite or being infinity means that the series converges for all values of x. And because we get this values, because we got this infinity right over here, that's telling us that the series is going to diverge for all values of x, which is not 100% true. We have to make sure we think. Okay, remember in our theorem, it was only one of three possibilities. So if you said as a conclusion that of getting infinity here that the series diverges for all values of x, that's not one of our three possibilities. That's false. Okay. But the fact that we get this going off to infinity means it's going to diverge for all values of x except at its center. This is the case for number 1. Okay. So the radius of convergence in this one is going to be 0 because the only value for which the power series is going to converge is at its center A. And that's actually 0. The center of this series is actually 0. All right, example number 3. Find the radius of convergence for the power series here. Sum from n equals 0 to infinity, 3 times the quantity x minus 2 to the power of n. Again, please pause the video and you'll give this a try to see how well you can do without me. Again, we're going to be using the ratio test. And so I'm just going right into setting this up. And it looks like this. The 3 is going to cancel here. This is going to cancel with this. And we're left with just an x minus 2 here in the numerator. So let's be clear about what we see here and not lose sight of the quantities that are changing. Don't forget the absolute value symbols because we still have x here, and x could be a quantity such that x minus 2 is negative. But we're taking the limit as n approaches infinity, and all the n's are gone. So this is just a constant. The absolute value of the quantity x minus 2 as n changes is not changing. So this works out to be just the absolute value of x minus 2. All right. What does that mean? Well, remember, we're using the ratio test, and so our conclusions that we draw have to come from the ratio test itself. And the ratio test tells us that the series will converge when that limit comes out to a value less than 1. Or we got this value here. So actually, I'll write this down. By the ratio test, this series will converge when the absolute value of the quantity x minus 2 is less than 1. So what's the radius of convergence then? To answer the question at the start of this, what's the answer to the question? Well, that's the answer to the question. That's R. Remember, if you go back to the theorem here, this is what we're dealing with right here. That's the interval of convergence. R is this value right over here. We get this quantity, the absolute value of x minus 8 less than R. We make it look like that, then we have our radius of convergence. And we have that. That's what this is right here. And so the absolute value of the quantity x minus 2 less than 1, that tells us that R is equal to 1. All right. I'm going to take this a step or two further, but not all the way to the interval of convergence. But I just want to interpret a little bit more what it is that this is telling us, okay? So, well, this should tell us something. This is our value of A. This is the center of our series, okay? So if I'm dealing with a series centered at A, whoops, we know A is 2, okay? And then we have a radius of convergence of 1. So what is our interval of convergence? Well, that means that I got to go 1 unit in this direction, and I got to go 1 unit in this direction. So if I just add 1 to 2 to get 3 and subtract 1 from 2 to get 1, then the interval of convergence, we know for sure that the series will converge for all values of x between 1 and 3. Now, this is where I'm going to stop going all the way to the interval of convergence. I don't know if the series will converge at 1. I don't know if the series will converge at 3 because I haven't done the test. I haven't tested those points separately, but I would have to if I want to know. But that's not the question. Didn't ask me for the interval of convergence, so I'm just trying to tell you what this signals to us as far as the values of x for which the series converges, and what we would have to do if we wanted to take it all the way to find the actual interval of convergence. So again, we know the center is 2 and the radius is 1, means I move 1 unit from 2 in both directions, and that will give me the interval of convergence, except for the endpoints, which need to be tested separately. All right, example number 4. Let's find the interval of convergence for the series, power series here. The sum from n equals 1 to infinity of x to the power of n over n. The fact that we're starting at at n equals 1 instead of 0 doesn't matter. We're just deleting. Actually, we're not even deleting a term. If we start at n equals 0, of course, we get division by 0, so we can't have that. All right, so now we're not looking for the radius, although we're going to need it. So it's a step in the direction. Go find the radius, and then continue looking for the interval of convergence, like we did way back in example number 1. All right, please pause the video and go give this a try on your own. All right, so what I'm going to do is start the ratio test, as we've been doing. So x to the power of n plus 1 over n plus 1. And this is where I'll divide by the fraction, multiply by its reciprocal, instead of writing it as a fraction. Things cancel here. This becomes just an x here. I can't cancel the n over the n plus 1, so I'm going to have to leave that as is. And so I'm left with the absolute value of n times x over n plus 1. And again, as n goes to infinity, the x is a constant. So if you want, we can think about doing some algebra here. Now, in a couple different steps that I don't want to continually make as we go forward, but this is equivalent to this here. The n over n plus 1 is a non-negative quantity always. X could be negative, so I got to put the absolute value on x. So it could look like this. And then, again, this becomes algebra that I don't want to continue to do in other examples, but just for now so you can see it once. Since x is not changing as n goes to infinity, it's a constant, I can factor it out like this. And then we're just taking the limit as n approaches infinity over n plus 1. And that should very clearly be 1 for that limit. And then this works out to be just the absolute value of x. Now, again, we have to use our ratio test to draw a conclusion. And so the series will converge when the absolute value of x is less than 1. And so just to note that in this example here, even though it doesn't ask for it explicitly, sometimes they do. On the AP exam, they have asked for both the radius of convergence and the interval of convergence. So you should be aware that you might have to state both in your answer, even though you have to find the radius to go find the interval of convergence. You must state it clearly that that's what it is, so I'm not giving credit to reserve. So make sure you state it clearly, please. So the radius of convergence is 1. Notice that there's nothing being added or subtracted from x in the absolute value symbols. So I know this is probably obvious, but this is the absolute value of x minus 0 is less than 1, which tells us that a is 0, or the center of this power series is 0. So then from looking, I'm not using my fancy tool to make the horizontal line this time, but if the center is 0, then I got to go 1 unit in each direction. So obviously the interval of convergence is going to be between -1 and 1, possibly including the endpoints. which I need to test separately. But I know any value within that interval the series will certainly converge. All right, so now I got to go test those endpoints. So if x is equal to 1, what does the series become? Well, remember, this was the sum from 1 to infinity of x to the n over n, which is just, if I plug in 1 for x, so it'd be 1 to the n, which is just 1 over n. You should recognize that. If x equals 1, then this is the harmonic series. Which diverges. And if x is equal to -1, then the sum, it becomes -1 to the power of n over n is the alternating harmonic series. Now, we've already proved that our alternating harmonic series is convergent, so we don't have to reprove it. Sorry about the sudden scroll there. It didn't respond to me. But we know that converges. So the interval of convergence is, okay, so it converged at -1, it diverged at +1. So it's the, whoops, I got it backwards. Converged at -1 and diverged at 1. So it's the half closed, half open interval, -1, 1.